towards the cloud. All right, so Bayes' theorem and our learning objectives. So first we're going to define and apply. Bayes' theorem. To calculate the probability of a hypothesis given our observations or evidence and prior knowledge of the probability of related events. So we know about stuff ahead of time, and we're going to use that to calculate the probability of some hypothesis. And then we're going to explore the utility of Bayes' theorem. And contrast it to another statistical paradigm, which we'll define as well. Paradigm it's called frequentist statistics. All right, before we get into Bayes, let's just do a quick review. We have our conditional probability rule. And that states that the probability of A given B, assuming that they are what? Well, let me just write it out first. This is the probability of A and B divided by the probability of B. Assuming that they're not mutually exclusive and not statistically independent. And we'll also review the theorem of total probability, which is if we divide a probability space and divide it up into all the possible events that can happen, and we define some event that intersects all of these in some way, then the probability of A is equal to all of these intersections, conditional probabilities summed together. So just the sum of A given EI times the probability of EI. We're going to use these two things together to create Bayes' theorem, to kind of derive Bayes' theorem. And I'll just note that I've posted a walkthrough video where I do another example, a word problem. So that's under week 2. So if you're, for the homework and bringing it all together, make sure you go take a look at that video. We walk through. It's a long problem, but we kind of do all this stuff in one place together. So conditional probability theorem, total probability, bring it all together. Okay, so let's get into Bayes' theorem. So Bayes was a statistician, I believe a pastor, Methodist pastor, or something like that. And back in the day, a lot of people dabbled in different things, right? You kind of think of it as a scholar. And kind of the historical way of thinking about things was you collected data, you calculate the mean. We're going to get into this kind of basic approach at the last unit that we do in class. But okay, so we got the mean of the observations. We can do some uncertainty analysis. We can do a t-test or a z-test or something like that, assuming our observations fit a normal distribution. And then we can tell you the probability that we observe something, or the probability that two things are different given our observations. It's very direct. It's called frequentist statistics. If a lot of our observations fall close to the mean, then we can say that the mean's pretty certain. If we see a bunch of observations away from the mean, we can say those two things are different. It's a very direct approach. He and others in his era were thinking that there's a lot of other ways to go about this. Then we can bring in other kinds of information, and we can use probability theory itself to come at this a different way. So I'll just kind of walk into it conceptually, and then we'll get into it more detail as we go. So say we have a hypothesis. And I'll use, we'll call it H. I'll write this out first and we'll talk about it. That we know is related to some events or some observations. That we observe. Or have prior knowledge of. So some example of this, and a lot of Bayes examples, or Bayes theorem plays out in the medical sciences with testing. So our hypothesis, I'll just write this out. So what is the probability of, just a very contemporary example of having COVID, given you have a negative rapid test? Sure, everyone has probably at this point taken a rapid test and tried to figure out what that actually means. So what would the hypothesis be here for this statement? Take a second to think about that. The hypothesis is that we have COVID, right? So do we have COVID or do we not have COVID? The test is not going to be 100% conclusive, right? Okay, so let's invert this question. And that would say, what is the probability so I guess start with this. So probability of H is equal to probability of having COVID, and then our event, or EI, is that we have a negative test. So what's the probability of this event, a negative test, given that we have COVID? So we're just inverting that. And this would look like the probability of EI given our hypothesis, right? So let's put these together in symbology. The probability symbology. So this would be the probability that we have COVID, our hypothesis is true, given that we observe, we got that negative test, times the probability that we have that negative test. And that's going to be equal to, given the multiplication rule, we can just flip that around. So the probability that we have a negative test, given that we have our hypothesis true, that we have COVID, times the probability of our hypothesis. So the multiplication rule allows us to do this. And then ultimately, this is what we want to solve for. What is the probability we have COVID given that we have this negative test? So we're just going to divide by that and bring it over here. And then our next step, we'll use the theorem of total probability. So we'll use this probability of E. We'll kind of extrapolate this out using the theorem of total probability. So this could be, just in this example, it's a binary example. So we'll say it's the probability of E given H times the probability of H plus the probability of E given not H. Times the probability of not H. So all that goes in the numerator. Let's pick this apart a little bit. So some terminology, and if you watch that video ahead of class, then they define these different parts of this. And so this is what is called the posterior probability. It's the probability of our hypothesis given essentially new information, right? The evidence of that test. This guy right here is called our likelihood. Which is the probability of the evidence given the hypothesis, right? What's the likelihood that we would have this negative test given that we have COVID? This term right here is called our prior probability. Or the probability of our hypothesis. This can be based on experience, data, experimentation, it can be based on opinion. This is where we kind of get the subjective information in. We're not just, and when you think about frequentist statistics, it's like, okay, we're going to collect the data and then we're going to fit a normal distribution to it, and then we're going to do some tests. And there's no subjectivity in there. And Bayesian statistics acknowledges that, well, we've got a lot of information. We're not just coming in totally blind. For example, in this particular example, we have this prior knowledge of how much COVID is going around the community, right? So 2 weeks ago, we're sitting around, I don't know how many cases a week, right? But hundreds and hundreds of cases. So the probability of having COVID, just in general, was much higher. We can use that information to update what is the probability of you individual having COVID. So prior probability, that's a really important one. And then finally, this whole thing down here is the probability of our evidence, or total probability of the evidence. This does not equal 1, right? It's just the probability of having a negative test. So it's not, if you're dividing by 1, that doesn't mean anything. So this is taking all the possible outcomes of the evidence. All right, now I'm going to give you just a short algorithm for how we can use Bayes' theorem to basically update and improve our estimates or our calculations of probability of a hypothesis. So step 1, we just do this this equation up here, right? We gather all the probabilities that we need to know, and we just say our posterior probability is equal to our likelihood times our prior of our hypothesis divided by the probability of our evidence. All right, and so we're going to calculate this posterior probability. In step 2, we take this posterior probability and we plug it into this prior. So we take a test, we get a result, and then we plug it back in. We do that whole calculation again. So I'll just write it out. We say we use the posterior probability we'll do an example of this later as the prior probability on step 2, and then this updates to update our posterior probability. So we're kind of refining our estimate of the probability that we have COVID. So going back to this example, if we were to, and we're just using the same equation again in step 2. Our first prior is what is the probability of having COVID just in Mesa County? So we can plug that in. That's helpful information, right? If it's a higher probability, then I don't know about you guys, but like, seems like every single one of my friends had COVID in the last 2 weeks or last month. So there's just a higher likelihood of having COVID, right? But then we actually have some more information. We took this test, we did Bayes' theorem, we updated the probability that we have COVID given some evidence. Now we have some data personal to ourselves. And so we can plug that in as a prior and then do the calculation again. That's going to update our estimate of do we have COVID or not. And that's why the idea of, okay, what happens if I take 2 rapid tests, right? Does that improve my knowledge of having COVID or not? And it can. And so this is a method for doing that. This is called Bayesian updating. Updating. All right, one little conceptual example, and then we're going to watch a video about how this plays out on a game show. So here's another question. What is the probability of a fire given that we see smoke? Where there's smoke, there's a fire. Maybe not always. And maybe we could say, what's the probability that a house is on fire given we see smoke, right? So let's write this out. I'm gonna start, and I want you guys to take a minute to kind of think about how everything fits given Bayes' theorem. So probability, what's our hypothesis first? Probability of fire given smoke. Okay, so this is our posterior. That's what we're trying to calculate given some evidence. And then go ahead and write everything out for Bayes' theorem based on the algorithm that I gave you earlier. So this is our hypothesis and this is our evidence. Okay, so using the Bayes formula or theorem, we would say the probability of smoke given fire times the probability of fire all over the probability of smoke. So it's a simple, silly example, but if we think about it, we can use some more information here to actually calculate what's the probability of fire given I see smoke. And we'll say, a fire that we don't want, right? What's the probability of fires in general? Like of houses burning down in general? Pretty small, right? Maybe a handful of times a year. Probably more than that. I know a firefighter, and every time I see him, there's another fire that happens. I'm like, okay, which actually is pretty common. They just don't write it up in the news that very often. So this would just be the general probability of house fires. So you see smoke, you're like, oh, a house is on fire. Well, the probability is pretty low that actually a house is on fire. What's the probability of smoke from all the different sources out there? Right? It's wintertime. We got a lot of wood burning stoves, maybe people burning trash or wood piles. It's a good time to burn your brush. And then we can say, what's the probability of smoke given fire? Do we have situations where we have a fire, but there is no smoke? Maybe really hot fire that just there's no smoke. So we can put all those pieces together and say, okay, it's not 100% that we have a house fire every time we see smoke. Okay, I'm going to, how about you guys take a minute or two to talk about yourselves and come up with another example like this, where you can apply it to Bayes' theorem. And Jaden, we can talk about it.
Sounds good. So I guess we could do something. The fire one is really relevant. I actually live in Superior, right in the neighborhood where the Marshall fires were. But we could do something along the lines of like that video that we had to watch of the math student given that they're shy, or maybe like a business student given that they're outgoing. You could do like a business.
How about engineering?
Yeah. Oh, in engineering?
Yeah. Well, what do you think there's some traits of an engineering students?
Probably also shyness, probably lots of homework. You could do something like homework hours given major.
Okay, so we have oh, there we go. Okay. So the probability that a student has to do homework over the weekend.
Yeah, exactly.
I like that. And then we say, so this would be is this the smoke or is this the fire? And is this our hypothesis or is this our evidence?
It would be the hypothesis.
Yeah, I think so. So it's the probability. So we'll just say of homework given our observation that they're an engineering student
Uh-huh.
versus the probability of homework given, I don't know who you want to, I think everyone's probably doing homework over the weekend.
Maybe less in the business school, but
Okay, given business.
yeah.
Okay. I like it. Okay, and then once you come up with that example, try to write out Bayes' theorem. I don't know. Jaden, did you get it down? Let's see. Probability of, you just
Yeah.
flip
So,
it, homework.
Probability of homework over probability of the business.
This is just 100%.
Exactly.
All right, what example did y'all come up with? Okay, that's good. Probability of a brain tumor given headaches. It's not a tumor given headaches. Okay, and then how about y'all? Given they're doing math tutoring? Oh, the MAV center. Oh, in the gym. Got it. Okay. So you're in the gym. What's the probability that you're an athlete? Everyone's an athlete. There's athletes and then there's athletes. Carrie says our dog is such an athlete. He can jump very high. He can jump over fences very well. But he doesn't train like most athletes train. Okay. So let's take a look at this video. This is a game show from way before my time. Yeah, this one's a little crazy. Make sure we got our volumes. No, it's Monte Carlo is different. We'll do that later.
Behind one door is a car. And behind the other two are goats.
Goats.
You don't know which door contains the car. Let's say you choose the first door. The host, Monty Hall, will then open one of the other two doors. He knows what's behind each door and always chooses the door to go. Monty now gives you a choice. Stay with your original door or switch to the other end of the door. What should you do? This question confused even PhD holder mathematicians when it was first published. So maybe you'd have better luck on the less popular Mandy Hill show, which features a similar problem, but with 20 doors. There's still just one car. Again, let's say you pick the first one. Your door very likely contains the goat, which means the other doors very likely contain 18 goats and one car. And you will now open 18 doors, knowing each contains it. Did you switch instead? It's still very likely that the car is behind these 19 doors. But it's not behind any of the doors that Mandy opened, so it's very likely to be behind just this particular door. So you should definitely switch to it.
Woohoo.
In fact, if you switch, you have a 19 to 20 chance of winning the car versus a 1 in 20 chance of death. Now let's return to the original problem. The same reasoning in the 20-door problem applies here. Your door is more likely to contain goat than a car. The other doors are more likely to contain goat than a car and 2 goats. So even after Monty opens the door of the goat, it's still more likely than not one of these doors contains a car, but only the unopened one can. So switch to it. Switching gives you a 2 in 3 chance versus a 1 in 3 chance if you don't switch.
Brilliant. Okay. It's okay. I've watched this like, half a dozen times now. What about that makes sense, or what about that doesn't make any sense? How is that? Is there something voodoo going on there? What's the information we have? Well, we have information from Monty. He went and opened a door, and he knew which door to open that had a goat. And so the way I kind of think about it is Monty inserted some information into the ether by making a choice. And we can use that information to make our choice, which is switching. And we can actually play the math out. So here's a figure that, and I'll post this, that does it, but I think we'll just write it out together, and then we'll kind of look at that figure. So let's just do that. I'd love to go back and see if they actually gave away goats, and if people actually took them, right? Because, like, I don't know, goats, they can serve a good purpose, right? Okay, so going into this game show, we have 3 doors. What's our prior knowledge just about this, how the show works? What do you know about the setup going into this? There's 1 car, right? And so we have our prior knowledge, and we'll call this A, door B, and door C. So we can write it out this way. So the probability that the car is A or B or C is equal to 1/3. We know it's behind one of these doors. I like that hot rod that they had up there. And then we can write this down as kind of, we'll just make a table here. So here's door A, here's door B, and here's door C. And we have our prior knowledge. Probability that the car is at A is equal to 1/3. Okay. And then we have this event happen. Doesn't matter which door we choose. How about we pick? Jaden, do you want to pick a door?
B.
All right. Okay, so Jaden chooses B. And then who wants to be Monty? Okay, so you choose B, or sorry, Jaden chose B. So which one are you going to choose? Okay, so Monty opens A, and there's a goat in there. We get a goat. My daughter can draw way better than me. It's got a little tumor there. Hope it doesn't have a headache. What's the probability of having a headache given you have a tumor? All right. So now let's write this out. Okay, so Monty opened A, we chose B. So now we want to know what is the probability. Okay, so the probability that we would open A given that the car is in what we chose, B. What's that probability? You chose B, probably that would open A. So if it, yeah, 50-50, it's just 1/2. Okay, now we go to oh, sorry. Let me just rephrase that. This is what happens when I open it up for improv. Okay. Okay. So so this is the okay. So the probability that Monty would. Let's see. Okay. Okay. So probably that Monty would open A given that the car is at A. That's 0. Okay. Good job. So he won't open it if it's there. So the probability here now we're at B. So the probability that he would open B given the car is at B. Or sorry, he opens A. So what's the so he opened A. What's the probability he opens A given that the car is at B? We chose B. So this is that 50-50. And then C, the probability that he would open A given the car is at C. He's not going to open C. He's not going to open the car, right? So that's 1. There's no choice there, right? Okay, so now we can update our probabilities. So we can say the chances of a car being behind each door given an event. So this is each door given the event. I'm just going to move this up real quick. Okay, so now this is like, all right, which door do we choose? So you chose B, Monty opened A. Do we stick with B or do we go to C? And so let's think about it this way. So what's the probability of the car at A given Monty opens A? So that's 0. What's the probability that the car is at B given that he opens A? that is equal to it's equal to 1/3. I'm trying to figure out why. Oh, okay. This is equal, there's some math that we'll have to do, so just a sec. So that's equal to 1/3, and then the probability that the car is at C, given that he opens A, is equal to 2/3. So let's actually do the math behind that, and we'll just do the two examples. So okay. So the first would be you stick to your guns. And you stay with B. Okay, so let's actually calculate. So the probability that the car is at B, given that you opened A, is equal to, and we're going to use Bayes' theorem here. So probability that we opened A, given car is at B, times the probability that the car is at B, divided by all of the potential options out there. So we'll say the probability that he opens B, given car, or sorry, opens A, given car is at B, times the probability that the car is at B, plus the probability that he opens A, given it's at A, times the probability of A, and then times the probability that he opens A, given the car is at C, times the probability of C. Because the car is at C. So let's add all these things together. We have the probability that he opens B, given the car is at A, and that was 1/2, times the probability that the car is at B, that's 1/3. And then the probability that it opens A, given the car is at B, that's 1/2, times the probability that it's at B, that's 1/3, plus the probability that it opens A, given it's at say, that's 0. So we're not going to do the rest of that. And then the probability that he opens A, given it's at C. And you chose B, right? So that's 1 times 1/3, the probability that it's at C. So if we do all that math, we get 1/3. And then we'll do it where we switch our choice. And so now we're going to calculate the probability that the car is at C, given that you opened A. Given that the car is at C. And then we're going to divide that by all of those things again, right? So the probability that we open A, given the car is at some door I. Which ends up being this same term. So now this equals the probability that it opens A, given that the car is at C. So we'll go up here. That's 1. Because you chose B, right? So now we have a bigger probability up here. So that's 1 times the probability that's at C, so that's 1/3. And then we divide that everything by 1/2 times 1/3 plus 1 times 1/3. So this is the difference. Instead of 1/2, it's 1. The probability, so you chose B. The probability that you would choose, they would open A given that it's at C is 1. So that's the knowledge that Monty has that brings it to this, and that's how we're able to update that. And so then you end up with 2/3 as the outcome. And the crux again is this right here. You chose B. He's not going to choose C if the car's behind there, so he's making a decision. He's giving you information by choosing A. So we just use Bayes then to calculate this 2/3 right here. And if we go to, so here's that figure that plays it all out. And then you can set up numerical trial simulations, right? So randomly you assign a car to a door, randomly you pick a door, Monty always picks the other door. And then now you can tell the program, okay, switch or not. So here is the switching choice every time they switch. And you can see that over 100 simulations, they get about 2/3, and then you don't switch over 100 simulations on average. It's about 1/3. So that's just the numbers. A little bit of voodoo, but it works out. Okay, so next time we will go over another example, a concrete example, literally, and because it's civil engineering, and talk about some more. So just so you know, I have posted lab 1. It's going to be due in 2 weeks. So make sure you take a look at that before Friday. We'll spend some time on it on Friday. And if you have any questions and stuff you want to go over, just we can talk. We have a couple minutes here.